Alrighty, good morning. This is Thursday, May 28th. This is period A2. Uh, this is AP Computer Science A. I hope you're having a great day so far, and I'm going to try to make it even better with talking about searching and sorting algorithms. Last class, oh, by the way, this is our final class together for seniors, members of the class of 2020. I'll have a little couple words to say at the end, but in short, thank you so much for your hard work and dedication. It's been a wild ride, and we're going to try to end it on a very, very high note today. What we started talking about two classes ago, and we really talked about in depth last class, were some different searching and sorting algorithms that exist in the world, the wide world of computer science. There are a lot more than the ones that I presented to you today, or the ones I presented to you on Tuesday, but these are the ones specifically that the AP Computer Science A exam normally focuses on, the ones that the textbook focuses on, the ones that the curriculum really wants me to identify and highlight for you. If you take any form of a computer science class in college beyond just introductory programming, you will most certainly talk about searching and sorting algorithms and all of the math behind it and all of the complexities and data structures and how it works and all that fun stuff. But my objective for a high school setting is really just to give you an overview of how these things operate, why certain ones are more efficient or less efficient than the others, and talk about the complexity time. I did mention that I made just two errors last class when I was talking about these sorting methods. For selection sort, selection sort is always order n squared. It is not just best case order n and then average case and worst case n squared. It is always order n squared because regardless of whether the list is already sorted, reverse sorted, if it contains duplicates, selection sort still has to go through the list and still try to, still has to go through the list n times and check each element's after every pass that it makes through the list. In other words, it has to pass through the list n times and make n checks for each time that it does so. Whether or not things are sorted, that just means nothing's going to get swapped. But the fact that it still has to go through the list once, and then it has to go through the whole list again, and it has to go through the whole list again, so it has to go through the list of n things n times. I also mistakenly said that quicksort's worst case is if the list is sorted in reverse order. That is not true. Quicksort's worst case is still order n squared. Quicksort's worst case is if the list contains multiple duplicate elements, because if it contains duplicate elements, what's going to happen is it's going to keep creating these partitions, it's going to keep creating these pivot points and trying to flip-flop things around, but since there's a bunch of duplicates, it's going to have to do that n times, as opposed to when it's in the worst case, or as opposed to when it's in reverse order, which is still order n log n. Okay, so that's the deal with quicksort. Just to very quickly go through these different searching and sorting methods to identify or to help explain, we have these lovely Uno card visual aids here. Let's first go through the searches. If I'm trying to search for a specific element in a list, and I know nothing about the list, I'm trying to find something that may or may not be in the list, and I don't know anything about it, unfortunately, there's really no better way than to do sequential search. Sequential search, hey, if you can think of a better way, I don't want to say there's no better way definitively. If you can think of a better way, then, you're on track to be Time Magazine's Person of the Year. It's not impossible, but there really isn't, to anyone's knowledge, a better way than to just start at the beginning or start at some arbitrary position in the list and just search one element after the other until you try to find what you're looking for, right? It can be like, is this what I'm looking for? 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 Is that what I'm looking for? It has a average case of order n and a worst case of order n. The worst case if it's at the end of the list, average case if it's in the middle. The best case is order 1. That's pretty rare, though. It just so happens that the data you're looking for is the very first one. That would be great, but not always the case. Binary search is way better than sequential or linear search, but unfortunately, binary search requires that your list is already in order. Okay, so sometimes sorting the list and then using binary search just takes longer than if you just did a sequential search. If you just do a sequential search, you just kind of have to suck it up that it's order n and deal with it. If you sort and then search, it can be a lot longer of a process. However, if you know that the data you're already receiving is sorted, or that sorting is just maintained throughout the process of your program. Like some of the FRQs we looked at in our class, we saw methods that sorted things as they went along. Like as the program is running, it's sorting in the meantime. So we know that those array lists of data are already sorted. Then binary search is way faster. And binary search exactly mimics the process of saying, like I said the other day, I'm thinking of a number between 1 and 100. What is it? You'd, of course, if you're intelligent, start with 50, and then you'd cut that in half, and cut that in half, and cut that in half until you identify it. That's exactly what binary search does. It starts at the middle. It says, are we looking for something higher or lower than this? If it's lower, it's going to search over here and check the middle element of this. If it's higher, it's going to search over here and check the middle element of this. And it just keeps going until it finds what it needs. Because of that, the average and worst case is order log base 2 of n, or you might just see that written as order log n. The best case is order 1 if it just so happens that the data we're looking for is right in the middle. So those are our searching algorithms. Not to say that there aren't any other searching algorithms out there. I'm sure you could think of some way. But it's interesting in that you're trying to think of step-by-step ways that you can tell the computer to search for something or sort data. It's not just human intuition that if I'm given a random list, I can be like, oh, let's just make a couple swaps here. A computer can't do that. A computer needs steps. We then took a look at some sorting methods, and I'll just go through them really, really fast. Selection sort, essentially what selection sort does is it goes ahead and goes through the entire list, tries to find the lowest element of the list. Once it finds the lowest element of the list, it puts it to the beginning, and then it checks again and puts it to the beginning and checks again and puts it at the beginning until the list is sorted. So the way this would work is it would go through the whole list, identify 4 as the lowest. It would then go through the whole list again, identify 5 as now the lowest, go through the whole list again, identify 6 as now the lowest, and then go through the whole list again and identify that 7 is now the lowest. Alrighty? So that's pretty much how selection sort works. Insertion sort is a little better than selection sort. Selection sort is a very basic, I don't want to say basic, it's a very like primitive method of searching. I guess that's a good word for it. It's very non-refined. It's very just brute force, not efficient, but it makes sense logically. Like from a logical standpoint, it's easy to follow, easy to teach, easy to learn, but not the most efficient or methodical way to do it. Insertion sort is a little better in its best case. What insertion sort does is it pretty much takes a list, and again, it just checks through that whole list to try to find what's going on here. So what insertion sort is going to do is it's going to insert elements around the list accordingly. That was not very specific. The way insertion sort works is it essentially just checks the individual data, and it says, well, let's try and find the elements that are next in line here. It's going to say, well, this 7 is bigger than this, 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 bigger than this. It's going to go here. 3 is lower than this. It's going to stay here. 4 is bigger than this. It's going to stay right here. 5 is bigger than 4. It's going to stay right there. 6 is bigger than 5. 1 is less than 6, less than 5, less than 4, less than 3. It's going to get inserted right at the beginning. 2 is less than 6, less than 5, less than 4, less than 3, but bigger than 1. It's going to get inserted right there. And lastly, 7 would be at the very, very end. So it essentially targets each element individually in the list and then just places it accordingly until that's all done. Okay? Now, again, it's average case and worst case is that occurs n squared times. The best case is if it's already sorted, because your list would say, oh, let's place 1 where it is. It's already there. Let's put 2 where it already is. It's already there. Let's put 3 in its best place. It's already there. Let's put 4 there. And it only goes through this list once, and then it's done. So the best case is if the list is already sorted. It's order n. After that, we had something called quicksort. What quicksort does is it establishes a pivot point and then tries to move everything around that pivot point. So for example, if I had the data kind of looking like this, again, I just kind of randomly shuffled all the cards in my hand. What quicksort does and the way it works, it tells the computer, hey, identify what the middle value is. It just takes this 3, it's right in the middle of the list, and move everything less than 3 to the left of it and everything bigger than 3 to the right of it. So what it's going to do, it's going to say 1, that's less than 3. 2, that's less than 3. 6 is bigger than 3. 7 is bigger than 3. 4 is bigger than 3. 5 is bigger than 3. Then it's going to go through again, and it's going to do the same type of thing. No problem, Gabe. I appreciate you coming on in. It's going to do the same thing again, and it's going to say, all right, well, let's split this list in half. It's going to say everything less than 2 over here, everything bigger than 2 over on the right. It's already kind of done, but what would happen is the 1 would actually just go to the left of the 2, and that side would be sorted. You see how it's 1, 2, 3 all in order like that? I know it's kind of going off the camera a little bit, but hopefully that makes sense. Over on the right side, what would happen is it would pick a middle element. It would be 4 in this case because it rounds up if it's an even number. And then it would say everything less than 4, get on the left. Everything greater than 4, get on the right. In this case, these would all go to the right. So you'd have something that looks like this. It would pick the middle element and it'd say everything less than, get on the left. Everything greater than, get on the right. These would all go on the left. And then last but not least, it would pick this element and it would move 6 to the right. So it's always picking that middle element and moving. And you notice that by the time we're done, we have the list in sorted form. It's a little easier to show if I have a larger working space, but you see that I have 1, 2, 3, 4, 5, 6, 7, all in order. Okay? Last but most certainly not least, the one we did not get to is merge sort. The way that merge sort works is it essentially breaks the data down into small arrays, very small chunks of arrays, and then merges them together. So it's sorting them as it does. So here's exactly how merge sort works. Ready? We're going to consider again just this random arrangement of things. Just like that. Okay? What merge sort does, the way it technically works, is it says let's group each element into individual pairs. So we're going to group each element individually. We have 7 into individual groups. 7, 1, 4, 5, 2, 6, and 3. What it does is it really creates, since this is an array, this data would be stored in an array of size 7, it creates 7 arrays of size 1. What it then does is it says, let's pair these together and sort as we do. So what it does is it looks at 7 and 1, and it's going to pair these together, and it's going to sort 1 followed by 7. It's going to pair 4 and 5, and it's going to swap them. Or sorry, no, it's not. It's not. It's going to preserve the order. It's going to pair 2 and 6. It's going to preserve the order. And this 3 kind of gets left on its own for now. Okay? Try to show everything on the camera here. Then what happens from there is it says, let's look at these 2 pairs and merge them together into a new list. So we started with 7 individual lists. I'm now down to 4 lists. And it's going to take these and try to turn them down into fewer lists. So what happens is we essentially look at this element and this element, and I say which one of these is smaller. The 1 is smaller, so that's going to come first. Now which one of these is smaller? The 4 is smaller, that's going to come next. Which one of these is smaller? The 5 is smaller, that's going to come next. And the 7 is the only one left. So we now have a list of 4 things. We look here and here at these 2 pairs. Which one of these is smaller? The 2. Which one of these is smaller? The 3. Which one of these is smaller? Obviously, it's the only one left, the 6. So now we have 2 groups, 2 sorted groups. And the way that it works is it's now just going to take these 2 sorted groups and do that same pattern. Start at the beginning of both, say which one of these 2 things is smaller. The 1 is smaller, so that's going to come first. Now, which one of these 2 things is smaller? The 2 is smaller, so we're going to come right over here. Which one of these is smaller? The 3. Right here. Which one of these is smaller now? The 4. Which one of these is smaller now? The 5. Which one's smaller? The 6. And then the last element is 7. And we end up with our list merged back together. That's why it's called merge sort, in a properly sorted order. Does that make sense to everybody how that works? So it essentially takes your list, splits it apart, and then pairs it up until it's all reassembled. Pairs it together in groups of 2, then groups of 4, then groups of 8 if there's that many elements, and then it would just keep growing and growing and growing till it's all sorted together. Okay? So what merge sort essentially does is it pairs up individual elements into larger and larger sorted groups until the whole list is sorted. Okay, that's what that does. All right, and merge sort actually has the same best case and average case of quick sort, but the nice benefit of merge sort is it is not order n squared in any case. We have order n log base 2 of n for merge sort. We also have order of n log base 2 of n here. And our merge sort actually does have as well order n log base 2 of n. Okay? Which is nice. Which is really nice. The problem is, though, you might be wondering, why not just use merge sort all the time? Merge sort clearly seems to be the best of the sorting methods. It's the most efficient, so why not just use that all the time? The problem with merge sort is that merge sort is very inefficient in terms of resources. Although, yes, it's fast in terms of comparisons, it does take up a lot of memory to be able to create all those independent arrays and then create new arrays to put them together. A computer can do that quickly, but it is not memory efficient to do so. So what happens is, on a lot of applications, that may not be super relevant now where memory is in abundance, but on a lot of applications like mobile apps where every bit of memory is precious, merge sort is probably not the algorithm you're going to see because it chews up just a lot of memory when it does what it needs to do. It's fast, but it chews up a lot of memory because it has to create like all these different arrays to store data and then more arrays to store more data, and then just it chews up a lot of space. So that's sort of the downside of merge sort. Now, there are others, like I said to you. There's heap sort, there's something called bubble sort, there's a ton of others. I can't even begin to list them all. So if you are curious, you can go ahead and look them up. I'd highly recommend it. I have a great site, though, that I want to share with you right now to actually showcase to you some of the things that we need to do. I did not update the date on our class here, our actual Computer Science A page. There we go. This site, by the way, I will post it on Classroom for you. If you look up sorting algorithm, like a visual of sorting algorithms, it's one of the first results that comes up. Toptal, T-O-P-T-A-L, .com/developer/sorting algorithms. Really, really great site. What it does here is it actually gives you all of the different sorting algorithms. Some that we haven't talked about: bubble sort, the shell sort, heap sort I mentioned. There's a different variation of quick sort. And it allows you to play little animations of what happens if you have randomly sorted data, nearly sorted, reversed, or a few unique, meaning there's a lot of duplicates. Okay? And you can see what each one of these looks like. Take a look at, and you kind of see how it works when you do that. We'll start with selection sort. Notice that what selection sort does is it's going through the list, it's finding the lowest element every time, and it's swapping it to the beginning of the list. Do you see that? Finding the lowest element every time. Notice how slow it is. It's slow, very slow, because it has to check n things n times. It's n squared. Very, very slow algorithm, right? Notice that even when something's nearly sorted, it still has to go through that whole process, which is where my error was existing before. It still has to check the whole list. Even if it's sorted, it's still checking the entire list just to make sure. Reverse is the same thing. Very, very slow. Checks the whole list, swaps to the beginning, checks the whole list, swaps to the beginning, swaps to the beginning, over and over and over and over and over. Very slow. Okay? Insertion sort is a little better. In its nearly sorted, notice, fast. See how fast that was when it's nearly sorted? Because that's only an order n algorithm. It just has to check, and it puts everything in its proper spot, and everything's done, right? But when everything's random, it does take just about the same amount of time as selection sort in order to do that. It goes element by element, and it finds out where is this element's proper spot in the list. Notice when it gets to this little thing down there, it moves it all the way up because it keeps checking all of those different calculations, right? You can see that both of these in a random order are about the same. They take about the same amount of time. Oh, sorry. Hold on. Oops. Both of these in a random order take about the same amount of time to do. Selection sort is much slower, though. Well, let me play that from the beginning. Selection sort, much slower. Do you see that? Still both considered order n squared algorithms, but look at how slow selection sort is. Pathetic. Pathetically slow. That's how slow it is. Okay? When it's reversed, notice how slow selection sort is. Super slow. Insertion sort, much faster. Still order n squared, but way faster. Okay? Next, the things we talked about were merge sort and quick sort. Notice how fast quicksort is compared to the others. It shows where those pointers are, where those partitions are, and how it splits the list in half. Compare selection sort and insertion sort to quicksort. Notice the speeds here. Notice the speeds. Quicksort's already done. The other two are still chugging away. Bubble sort's also very slow. Still chugging away. Still chugging away. Finally done. Right? Notice when you're nearly sorted, or sorry. I'll play all these. Insertion sort was really fast because that's only order n. Quicksort's a little slower, order n log n. And then selection sort, very slow, order n. Okay? Cool. Notice the worst case of quicksort, though, when you have a lot of duplicates, quicksort is very slow in order to identify proper pivots and move things around. See how slow that was? But selection sort, still slower. That's the thing. Selection sort is terrible. Never bet on selection sort. Okay? And lastly, the merge sort is the other one I want to show you. Notice how merge sort works. It's pairing elements together. It's kind of hard to see in the visualization, and then arranges it all in one final group, right? Pairs all the elements together. It's grouping, and then it merges it all together in one final group. Okay? You can click on each one of these types of things, and you could actually see all of the code behind it. So this code, I believe, is written in I think it's written in JavaScript, but you could probably follow the logic along and figure out how it works. So this is the code for insertion sort. Just says go through all the elements until you reach the end of the list and swap if you need to swap, if that's true. Okay, so that's pretty cool. It talks about it gives you a little description. It gives you properties about it, and it tells you, what you need to be able to do in order to make that work. Okay. Again, I'll post this on Classroom. Actually, I'll post it in the Meet right now. I highly recommend checking this out. Ooh, the picture within a picture within a picture within a picture within a picture. I'll post that in the Meet right now. I highly recommend checking that out because I think it is a great. Where am I going? Right here. I think it is a great resource for you to help describe all of these searching and sorting algorithms. Okay. You can also play them all at the same time and see which one's going to be the fastest. Do you notice how quick shell sort, heap sort are? Those are a lot more complex to understand. But the more complex the algorithm is, a lot of times the more efficient it is. It's just harder to logically process. Okay, pretty cool. So I highly recommend checking that out. Definitely really cool. Okay, you could see that you can increase the number of elements. You can make it a ton of elements. And then you could really start to see the differences between them. When you have a ton of elements, look at how fast insertion sort was when we were neatly sorted. Look at the others being still pretty slow. Merge sort's still going. Quick sort's still going. Selection sort, poor selection sort. Selection sort isn't even close. Isn't even close. We're going to be sitting here for a while. So, poor thing. Don't use selection sort. All right, anyway, we're not going to sit here and wait for that to finish. That'll take forever. Does anybody have any questions on our sorting algorithms? Like I mentioned before, I'm not going to assess you on this, and the reason I wanted to present it to you was because it would be remiss of me not to do so. It would be something that I expect you to have exposure of after leaving the AP Computer Science A class, and I think it's good information to have going into a college computer science engineering program, any of those types of things. You will be expected to have at least a basic understanding of what these things are and how they work. So I definitely wanted to share that with you, as well as the complexity times. Does anybody have any questions for anything that I've mentioned today? Feeling good? All right, couple quick reminders. Your final project is due technically Sunday night, so if you need to get that, if you need to take it the weekend to get it done, please make sure you get it done. I'll make sure I grade it for you. I mentioned that it is going to count as 2 progress assessment grades, so it'll make up a third, I believe, of your fourth quarter grade. So it's a big deal. Don't try not to stress too much about it. I understand we're in a distance learning environment. I understand that it's been difficult to probably work together on it. Not that I'm holding my expectations low. I don't want to paint that picture at all because I know that you guys are capable of fantastic work being an AP group. But that being said, if you don't if you're not able to put all the bells and whistles on your program that you may want to, I'm not going to penalize you for it. All right, I understand that the environment in which we're working now is very different to if we were in school, and we'd probably have about like at least 3 weeks of in-class time to work on the final project. So there would be an abundance of time, not the case in our current environment. So I get it, but still, I am expecting a pretty nice final project. Okay. All right. If you have any other questions for me, please feel free to let me know. Other than that, I hope you have a great rest of your day. I want to again thank the seniors for all their hard work. Hopefully, I think it's bittersweet when you get to the end of your senior year. I remember for me, at least, when I was a senior, I was very excited to get out of school, but I think it's a little bittersweet. Mostly sweet, because I'm like, it's done. Maybe some of you aren't able to do that yet. I know some of you are still working very hard, so I don't want to make it sound like you've reached the end of your goal already. But it's like, oh man, it's done. It's a relief. I don't have to worry about that anymore. And it feels good. But at the same time, you're like, I'm going to miss my friends. I'm going to miss certain things about school. So hopefully we've been able to make this a great experience for the seniors. And I'm sure I'll have very similar words to echo to the juniors and do we have sophomores in here? We do. The juniors and underclassmen later on. All right. But I just want to say again, thank you for everything. If you ever need to reach out, I'm always available for you. So please do not hesitate to contact me with any questions or concerns you have. And I'll see you guys next week, next Tuesday, for our last week of classes. So bye, everyone. Have a great day, and I will see you then.
Have a good day.
Bye, Mr. Giorgio.
Bye,
See you,
Mr.
Giorgio.
Giorgio.
See you later.
Yeah.